One specific example of a double displacement reaction is a neutralization reaction. This is when an acid, proton donator, and a base, proton acceptor, are both present in water. As a result, they will neutralize each other. The donator will give to the acceptor, and they will take each other out and just form water. An example here would be sodium hydroxide reacting aqueous, reacting with hydrochloric acid, aqueous, to form sodium chloride, aqueous, and water, liquid. That's an L. Okay. So what we can see here is the proton was donated from him to form the water, and the remaining ions stuck together. This is sort of our old way of representing these kinds of reactions, and we've talked earlier about how it's more useful to talk about them as ions. So if I write this out instead as an ionic equation, we can see what's happening here a little bit more carefully. So instead of writing sodium and sodium hydroxide, I can write sodium and hydroxide. I need to be a little bit careful here. This HCl, when it dissolved in water, didn't actually form H+. What it really did, we've talked about this before, is formed hydronium and Cl-. So if I write out its ions, I should really write out H3O+, aqueous, and Cl-, aqueous. Now, what happens here is that these two react in a meaningful way, and these two represent our spectator ions. So, sodium is left unchanged after the reaction, and chlorine is left unchanged after the reaction, and H3O and OH react to form two water molecules, liquid. So we get a formation of water when the hydrogen is donated from the hydronium to the hydroxide, and we have spectator ions, which were there in the original crystals of the acid and base, but aren't effectively involved in this. In this reaction, we always say then that we get a salt and water. So an acid and a base in a neutralization reaction result in a salt and a water. I think it's useful, or I think we should write the net ionic equation here, OH minus plus H3O plus, to realize that it doesn't really actually in any way matter which acid or which base are engaged in this acid-base reaction. This is going to be the resulting net ionic equation regardless of the acid and base involved. Let me give you one more example of an acid-base reaction, and we'll see how that's the case. Let's say we had HNO3, and that's going to react with lithium hydroxide. Actually, let's make it even a little more complicated. Let's make that ammonia. In our old way of representing this, we would say that this is going to form water and a salt, but in this case we're just going to get the salt, NH4 NO3, and we just assume all of it's happening in water. But let's look at what's really going on here. Really, HNO3 is reacting with a water molecule to produce H3O plus and NO3 minus. Similarly, NH3 is reacting with water to produce NH4 plus OH minus. The full ionic equation then, when these two things react with each other, is that H3O plus NO3 minus is reacting with NH4 plus and OH minus to produce NO3 minus, spectator ion remains unchanged, NH4 plus, spectator ion remains unchanged, and 2 water molecules. So if I take out my spectator ions, then I get left with the same real net ionic equation for a neutralization reaction. And this is true for any acid and any base that you consider. When they react, this is the net ionic equation. The real meaningful thing is that one of those things created hydronium. The other one created hydroxide. The hydronium and hydroxide are reacting to form water. This is very exothermic. Let's try that again. Exothermic. Spontaneous, and this reaction happens right away. These ions then just float around in solution. Our old way of representing them shows them as a salt, but our new way of representing them realizes that they're actually just ions remaining in solution and that they don't really form a meaningful salt. This is the only real meaningful reaction that happens.